So we have this. So now we went from our vector equation, like this, to here. So this supposedly contains the same information. It identifies our line. But here, what do we call this? We don't call it a vector equation, but we still call it a set of parametric equations. Why? Because it's in terms of some parameter. Remember, we have x equals some function of t, y equals another function of t, and z equals another function of t. So this is called a set of parametric equations. So we were able to write a vector parametric equation, which is nice in and of itself, but we also see that that generates a set of non-vector parametric equations. And this is for the equation for the line that we were seeking. Okay, so we got a lot accomplished, and these parametric equations work just as well in R2, that is if we ignore this one, or in Rn, where n is arbitrary, so we could do this. And this will be the given an A1 and a B1, an A2 and a B2, and so on. This will be the equation for a line in Rn. Okay, let's have a little practice of all of this. So what do we mean by practice? We want to be given some information and then find the vector equation and find the parametric equations. So in other words, we're going to identify a particular line. They're going to give us a particular line. They're going to give us information that specifies a particular line. And then we want to write the vector parametric equation. And we'd also like to generate those parametric equations for the line. Okay, so let's try it out. To find the parametric equations, so that they're specifying this as the end goal, but we're going to first get the vector equation. So a vector equation of what? Of the line through this point. So we have to be given a point, and they're giving us a point, and parallel to some vectors. I don't know why they have to give us such strange coordinates here, or strange constants here, or strange coefficients like pi. But anyway, that's all it is. It's just some coefficient. Sort of seems unnecessarily confusing to use pi here. Why don't we just have like a number like 5, but whatever. Okay, so again, we're given a point that goes through our line, and we want the line to be parallel to some vector. In this case, it's this vector. So to get the vector parametric equation is probably not too hard. Remember that the vector parametric equation just looks like this, and we're given some constant, some point that it goes through, and some vector that it's parallel to, and this is called the vector parametric equation. But we also sort of wrote it out a little bit more here, like this. So we had same R on the left, but then we wrote B like this part here. So we had B there, and then we wrote A like this part here. Okay, so we're going to do it that way. So we're going to write R on the left, and then B, and then the vector that we want to be parallel to the line. So we have here is B, this part here, so we put that here. And then this is the A that we want it to be parallel, so we put that here, and that's all. So now and then we can collect what multiplies the I's, which is this part, what multiplies the J's, which is this part, and what multiplies the K's, which is this part, and that's the way they leave it for the vector parametric equation for this line that we're seeking the equation of. And now they said the final goal, though, is to find the parametric equations. So not the vector parametric equation. We want the three of them. And these are the three. And how do we get that? We just associate. This is the x coordinate. So we say x equals this part, y equals this part, and z equals this part. And then we get this. So this will give us points on the line that they were talking about. This will give us points on the line that goes through this point and is parallel to this vector. So let's just make sure that it goes through this point. Let's just check that. I don't want to check that it's parallel to this, but let's at least make sure that it goes through this point. So how do we do that? We just want to find that there's a t that will generate this point. So some t that when we put it into here will give us this x, some t that when we put it into here will give us this y, and some t that when we put it into here will give us this z. Maybe I don't want to do that. So we're talking about 1 equals pi t plus 1, negative 2 equals this minus that, and 3 equals t plus 3. Okay, I don't want to do it because we'll have to solve for t. And I'm not sure if it's so easy to solve for t, so let's not do it. Okay, so now we have a methodology for finding vector equations of lines and also of getting the parametric equations of a line. And we could do it for all kinds of examples. And here they give another example. They tell us they try and specify a particular line, and then they ask us to generate the vector parametric equation and the corresponding parametric equations for the line. And they get an answer, and you can go through and read this yourself. Okay, after they finish that example, they say, example 4 brings up an important point, namely that parametric equations for a line, or more generally any curve, are never unique. So in the previous example, they showed this, and they showed, oh, actually, we could use this set of parametric equations, or we could use this set. So a reason for that is that of course, we always are talking about specifying a vector that the line is supposed to be parallel to, and we've called it A. And suppose we had this as our A, but then, of course, any multiple of A will also work just as well. And so we're going to end up generating, if we use a multiple of A instead of this particular A, we multiply all these by some constant. So like we multiply everything by 2, so then we'd have 2i minus 14j plus 8k, and that's going to be still in the same direction. We've talked about multiplying by a scalar doesn't change the direction, but that's going to give us a different set of parametric equations. So she brings up this question. If parametric equations are not determined uniquely, then how do you check your work? In general, it's not so easy. But in the case of lines, so in general, generally for curves, if you get parametric equations for curves, which we haven't really done yet, well, we did do it for the circle, but not generally. So in general, this is not so easy to do. But in the case of lines, there are two approaches to take. So one, she says, is to produce 2 points that lie on this line specified by the first set of parametric equations, because we said we want to check, like, are both of these true? Are both sets of parametric equations true? So we can find 2 points that lie on our first set of parametric equations, and then see that these points also lie on the second set of parametric equations. That's one way to check that if we get two different sets of parametric equations, that they both specify the same line, because if they both contain the 2 points on the line, then they must specify the same line. And by the way, note that that's even true in 3 space, or I guess in 4 space, and so on. So you still only need 2 points to determine a line, even in 3 space. So that's one way to make sure that your sets of parametric equations are talking about the same line. The other approach, she says, is to use parametric equations. So we have parametric equations to find what is called the symmetric form of a line in R3. From the parametric equations in number 2, which was back here, from these parametric equations, we can solve for each of those in terms of t. So we can solve the first one for t, the second one for t, and the third one for t. And this is what we'll get. So we've solved the first one for t, the second one for t, and the third one for t. But then, since they're all equal to t, they must all be equal to each other, which looks like this. So this is called the symmetric form. So in the example 4, which we didn't go through, where they got two different sets of parametric equations, these were the two symmetric forms that were generated, but they're saying basically these are the same forms, because they say that if you add 1 to each item in these 3, you'll get this. By adding 1, they mean, for example, if you're going to add 1 to this, you would add -1 over -1 to this. Is that right? No, I'm sorry. You'd add -1 over -1 to this, and you'd get this. And you'd add -1 over -1 to this, and you'd get this. Sorry, you'd add 7 over 7 to this, and you'd get this. And you'd add -4 over -4 to this, and you'd get that. So they say in general, symmetric forms for lines can differ only by a constant term or a constant scalar multiple, or both. And then they say that there's 2 equal signs here, so really we have 2 equations, and they point that out here. Okay, then they continue with a few other examples, just using these techniques. So in this case, they say we want to find out where a line that has these parametric equations intersects this plane. So I'm not going to go through that, but you can check it. And then another one. They say this is the parametric equations for a set of parametric equations for one line, and this for another. And so we could ask, where do these 2 lines intersect, if they intersect? So to mean that they intersect means that they have some point in common. Okay, so here are some exercises if you want to practice. And if you have the book, you can check the answers, or I think it's the odd numbered ones, at the end of the book. Okay, the last section we want to cover is the dot product. So they say that we already talked about how to add vectors, and also how to use multiply by a scalar. But we didn't talk about multiplying 2 vectors. We talked about multiplying a scalar times a vector, and we talked about adding 2 vectors, but we haven't talked about multiplying 2 vectors. So there are various ways that they do this, that we define this, but one of them is called the dot product. So here's the definition of the dot product when we have 2 vectors in R3. we have one vector in R3 and another vector in R3. And what do we mean by the so-called dot product? This is the notation for multiplying A and B in a certain way. And this is the mean. So it's very simple. We just take the first element of A times the first element of B, A1, B1, and then the second element of A and the second element of B, A2, B2. And so with the third element of each, and then we just sum them up. If we do it in R2, we wouldn't have this third term. We'd only have these first two terms. So one thing that it's important to note is that when you take the dot product of two vectors, you don't get a vector as the result, because this is just a number, right? A1 and B1 are both numbers, so when you multiply them, you get a number. And same thing with A2 and B2, you get a number. And same thing with A3 and B3, you get a number. When you add three numbers, you get a number, not a vector. So the dot product gives you a number. So you don't get a vector. So as an example, suppose we have this element here and this element here, I'm sorry, this vector here and this vector here, and you do the math and you get 15. So the dot product of these two vectors is a number, the number 15. And here we just write a vector in a different way and a vector in a different way. Now notice this vector doesn't have a j component, but we assume that the j component is 0. So we take 3 times, this has a 1 in front of it, and we take 2 times the j component here is 0, and we take -1 times the k component here is -2, and we do all of that, and we get 5. So the dot product of these two is 5. Again, it's not a vector, it's just a number. Okay, so once we have a definition for the dot product, we can prove various properties of the dot product. One is that if you take the dot product of A times itself, it has to be, it cannot be negative. It has to be either 0 or a positive number. And you can see that if you take A times itself, you're going to be taking the first component times itself. That's going to be, for example, 3 squared. This is going to be 2 squared. This is going to be -1 squared. So those are all positive. So when you add them up, you're not going to get a negative number. So that's the kind of argument that shows the idea that it's never going to be negative. Another is that you can reverse the order. You can commute these. So A dot B is the same as B dot A, and that's pretty clear. For example, if we do this one here, if we put this one over here, then we have 2 times 1 instead of 1 times 2. That's not going to make any difference. And the same with all the other components. So you can reverse the order, and it doesn't matter. Same thing here. This is like a distributive property. So I won't try and prove that, but maybe they prove it below. And then Ka dot B is Ka dot B. So you can do the K times the A first, or you can do it at the end, and so on. So here A dot A is this, and that's not going to be less than 0. Okay, and they say that we leave the proof of the other properties as exercises, so you can try and prove the other ones. Okay, so we just saw that A dot A looks like this. And also, if A is only 2-dimensional, then it's going to look like A1 squared plus A2 squared. Okay, so we know that if you have a vector like this or a line like this, and you want to know the length of it, we know that you can use this formula, the Pythagorean theorem, which is A1 squared plus A2 squared, and take the square root. And if you had 3 dimensions instead of just 2, the distance would be this formula, where this would be the third dimension component of that line or that vector. But we also just saw earlier that if you take A dot A, you get exactly what's inside here. So we're going to define what we mean by the length of a vector. And usually we just have one bar here and one bar here. So let's just imagine we just had that. Skip the double bars for the moment. Then we would say that the length is the square root of what's inside here. But we just saw that the square root of what's inside here is the dot product. That's what we get. We get this. So we can say that the length is the square root of the dot product. So as I said, ignore the double bars here for the moment, and we talk about the length of A is this. Now we do denote it like this, and that's, we don't use just a single bar because we want to define this more generally, not just for 3 dimensions, but maybe for 10 dimensions. So this sort of stands for the length even in 10 dimensions. And what we say is that the length, it's also called the norm or the magnitude, is A dot A, the square root of A dot A. So this is the general form for the magnitude of a vector, even if it's in more than 2 or 3 dimensions. But in 2 or 3 dimensions, it's just, we can just have one. We don't have the double bars. But anyway, this is the formula for the length. So we see that we can define the length in terms of the dot product, the square root of the dot product. We also, again, we call it the magnitude or the norm. Norm is spelled here, N-O-R-M. So of course, if this is true, then if we square the norm, we're squaring this so we get rid of the square root. So we get that A, and then I put that over here, put this over here. So we get A dot A equals the norm squared, or the magnitude squared, or the length squared. Okay, so we just showed that this is true, that A dot A is the norm squared. So what about something like A dot B? Well, maybe it's the norm of A times the norm of B, because this one is sort of in that form. If you have A dot A, we could sort of say it's the norm of A times the norm of A, right? That's what this is, the norm of A times the norm of A. So A dot A is the norm of A times the norm of A. Maybe A dot B is the norm of A times the norm of B, sort of following in these footsteps. But it's not exactly true. So we'd like a formula for A dot B and maybe write it something like this, but instead of the norm squared, it might be the norm of A times the norm of B, but it doesn't quite work. So what is the right answer? So A dot B is the norm of A times the norm of B, but there's an extra factor in here, which is the cosine of the angle between A and B. What do we mean by the cosine of the angle between them? Well, suppose we have an A here, and then we have another vector B, and we're going to put that B so that its base and A's base touch, so there's an angle between them. So that's the angle here. So A dot B is not as nice as just the norm of A times the norm of B. We have to include this extra factor here, the cosine of the angle between them. Now, we do know that there are times when the cosine of the angle between, the angle of it can be 1, right? The cosine of some angles are 1. What angle? When theta is 0, then the cosine of theta is 1. So in that case, if the two vectors have 0 angle between them, in other words, if they point in the same direction, then it does just work out that A dot B is the norm of A times the norm of B. And that's precisely what happens here, right? A is, of course, in the same direction as A, so the angle between A and A is 0, so the cosine will be 1, so we're just going to get the norm of A times the norm of A, and that's what we get here. So this is kind of a more general formula than this. And this is a specific case where we're talking about the same vector, and of course in that case that angle between the vector and itself is 0, and so the cosine will be 1. So anyway, this gives us a formula for A dot B in terms of the magnitude of A and the magnitude of B and the cosine of the angle between them. Okay. So this is what we just said, that A dot B is equal to the magnitude of A, or the norm of A, times the norm of B, times the cosine of the angle between them. Okay, well we can take this part here and bring it down to the denominator over here, like this. So we get the cosine of the angle is equal to this. And then, you can take the inverse cosine function, whatever that means, but anyway, you can take the inverse cosine. The inverse cosine of the cosine gives you nothing, so you just end up with theta on this side, and we're taking the inverse cosine of this side as well, so we get this. And this is a kind of very interesting result. What does it say? It says that the angle between two vectors is given by this formula. Well, that doesn't sound so interesting actually, but there's one point that's pretty good. So, we did this when A and B were like two-dimensional, right? We saw that picture like here. And we could sort of imagine this also in, maybe we could sort of imagine it in 3 dimensions, but actually, let's just say that we've considered it in 2 dimensions. But remember that the dot product itself is not necessarily restricted to 2 dimensions or 3 dimensions or anything. A can be any dimensional, n-dimensional, and B, of course, has to be the same, has to be n-dimensional to have this work. But so they can be, but we're not restricting ourselves just to 2-dimensional objects. So we can talk about n-dimensional objects here. And the norm, there's no problem. We even said that the norm is sort of a generalized absolute value for higher dimensional objects. So the norm has no problem with regard to having higher dimensional objects. So what's so good about what I just showed, which is here, is that this we will say is generally true. So what's so interesting about that? Well, if we have 2-dimensional objects like A and B, then there's no mystery about what we mean by the angle between them. But if we have 10-dimensional, if A and B are 10-dimensional, right, there's no angle between 2 vectors that are 10-dimensional, because angles are for 2-dimensional objects, not 10-dimensional objects. There's no notion of angle. But we can just take this formula, which works for 2 dimensions, and say, okay, then what do we mean by, or we can say this does hold for any dimensions. And so now we kind of have a formula for the angle between n-dimensional vectors. So that's kind of interesting, kind of fun. Now, don't think that this is like a real angle. It's not that. But we can say in a kind of a generalized way, we can say that the angle between, let's say this was a 10-dimensional object and this was a 10-dimensional object. What do we mean by the angle between them? Well, we can just use this formula. All of this stuff on the left works no matter what dimensional objects we're talking about. So we can calculate all of this stuff on the left, and then we can say, oh, well, that's the angle between these two 10-dimensional vectors.